disappeared. There's Tanuj. Hi, Tanuj.
Hello.
We're having technical difficulties. The meeting just automatically decided to end itself. So
Classic.
yeah, we're gonna wait a sec.
You're back on.
I'm back on. Okay, and is my screen sharing?
It is now, yes.
Cool. So good.
Yeah.
Okay. I guess for those of you on the recording and on Zoom, I'm the systems lead, and I just went over the requirements. I guess let's restart.
Yeah.
Okay. I'm only going over changes for requirements and ConOps because neither of these things have changed significantly since the PDR. So the only change in requirements is adding the sixth requirement, which states the rocket shall deploy 500 milliliters of water at or after apogee in the air that demonstrates safe ballast. And this is because FAR released their requirements in between PDR and CDR, and it said that the water release was a requirement instead of additional points. And this will be validated by analysis here at Cal Poly and also demonstration at the FAR competition. Oh, cool. Cool. Next up, we have our ConOps, which is, again, nearly identical to the PDR, so I'm not going to go over it in detail. The only change is that we have the water deployment at apogee in stage 4. The next 2 slides are also just a more detailed ConOps, and once again, the only change is the water ballast deployed, but I can stay here and have you look if anyone has any questions on the phases. Again, ConOps phase 2, nothing has changed on this slide since PDR. I'll pass it off to the aerodynamics team.
I'm back. I'm Ryan again, aerodynamics, and me and my team are going to present on some design profile stuff and analysis of that profile. So we're going to consider stability, performance, and manufacturability, as well as performing analysis on different simulations and conditions such as wind, angle of attack, temperature. So let's get that started. Yes.
Before you move on in the nickel content, you said there would be some budget.
Yes. Sorry, yeah, that has been moved to the end because I thought it made more sense since each section goes over their own individual budget. So then at the end, we bring all those together and show the total. A schedule, yeah. Yeah. I don't think the schedule is like fully complete, but we are working on that right now, and we have an estimate of how long that will take to complete manufacturing of our rocket. Okay, here's another overview, kind of like the table of contents. First is the profile manufacturing section, and that goes over all the dimensions of the nose cones, the body tubes, and the fins. After that would be flight performance, and that has a MATLAB function and open rocket model. I don't know if CFD because Jack is not feeling well. So angle of attack and then weather. Let's get started with profile manufacturing. Here is the overall model. Like I said earlier during the open rocket section, it's over 7 feet long. It's about 55 pounds total. And next up is going to be Tyler to present on the nose cone.
Hello, everyone. I'm Tyler. And so this is the redesigned nose cone. Before, we were going with one piece of carbon fiber wrapped around in a conical shape, but due to the payload deployment of water that's not required in the competition, we've had to modify our design a little bit, so now it's a 2-piece design. So this top piece is going to be made out of solid aluminum, again with a conical shape, manufactured on a manual lathe for simplifying for like a Von Karman nose cone. That's going to be a lot of hard manufacturing, just a simple angled cut. And we're going to have a 1/4-inch threaded hole in the bottom that will help attach to the rest of the system, which I'm going to show later. Next is the nose cone transition. This is the piece that's going to be holding the water in on the way up, as well as providing the majority of the structure for the nose cone. It's going to be made out of 6 layers of carbon fiber, and we're going to do a wet layup because we haven't been able to design a way to wrap this, vacuum seal it, and put it into the autoclave. So it's just going to be a wet layup. And we have this little shoulder piece that's also carbon fiber that's going to allow us to bolt into the top of the payload, or the top of the recovery payload, or recovery coupler, sorry. So for how these are going to kind of work together, we're going to have the nose cone tip bolted to this retainer disc that is going to be made out of any material we want. We're going to start with the 3D prints, and then we're going to test this with the expected accelerations that we're going to face to see if 3D printed plastic will be strong enough. If not, we can up it to like water jet cut steel. So on the way up, the nose cone tip is going to be held in by the aerodynamic forces and the acceleration. And then on the way down, as either the recovery system deploys or just as the rocket tips over after apogee, the nose cone tip will simply fall down, and the retainer disc will ensure that the nose cone tip doesn't fall several feet into the soil of the Mojave, while still allowing the water to get past and fully deploy. I'm going to pass this on to the next system, recovery.
Hello, I'm Juan. I'll be doing the tubes and fins. So first up, we have a recovery tube. Material is still on a carbon fiber. Length is 27.559 inches. And some other stats like our inner diameter is 6 inches, and then our wall thickness is 0.091 inches. That's changed, right?
Yeah, that has
Yeah.
changed. That's a little thicker based on what structures has told us.
Yep. So manufacturing is going to be pre-preg on an aluminum mandrel, and right for here we say 8 layers, but this is subject to change depending on which material we end up using. Alright, avionics like is fiberglass. That's kind of change, or not change, but material's different because avionics needed to be different for their stuff to work. Dimensions 15 inches long, inner diameter 6 inches, and same wall thickness of 0.091 inches. So we've changed from doing a pre-preg to now wet layup because testing results are fiberglass weren't the best. So now we will be doing wet layup. Yeah.
There'll be more on the testing during the structure section.
And then last for the tubes, there goes the mouse. Motor body tube. Material is still carbon fiber. The length is 33.071 inches. Inner diameter again 6 inches, and the wall thickness is, as always, 0.091 inches. And there it goes again. Okay. I'm not. Yeah. Again, pre-preg and 8 layers, or I guess not 8 layers, but trimmed by testing. Fins. New fins. Material is carbon fiber. Here is measurements: 11.811 inches for the root cord, 7.874 for the tip cord, height of 5.75 inches, and thickness of 0.138 inches. More measurements for the fin tabs. After running through our MATLAB sim for the flutter safety margin, we found it to be Mach 1.3805. And then, so for manufacturing, we'll be doing, so the fins will be fit on this large plate. They'll be manufactured through pre-preg and then cut on the water jet, and then fill it epoxy to help smoothen them out.
And one more thing, that used to be a sandwich layup, but this is now just pure pre-preg because the fins are thinner. So it wouldn't make sense to use the sandwich for bulk. Also, the epoxy fillets will be smoothed out using a concave cutter that our manufacturing lead got, so that we don't have to just sand it by hand anymore. Okay. Thank you, you too. And we're moving on to flight performance now. Target, yes, well.
Going back to the previous section. So you mentioned that the layers would change based on, like, they are something to change, like.
Which one?
All the body.
All of them?
Yeah, what were these layer, calculations?
Yes, so these layers were calculated based on the actual testing of the carbon fiber body tubes that we made. There were 3-inch body tubes that were about 8 inches and 4 inches. And we did the layers based on that calculation. However, the results of that testing was not promising. And we are talking with somebody or with a company about getting more donated. We just have to get somebody to drive down to Huntington Beach and bring it back to us. That is expired. It was for SpaceX, I believe, and they offered us 4 rolls of it. So that should be better than the stuff that was in the freezer, because you'll see during on the structures section, there's a slide of the results of the testing, and it shows that it is not ideal. So that's about all I can say on that. Yeah, the layers are calculated based on the physical results of what we made and how thick that was, how many times we wrapped it around, then divided to figure out the actual individual layer thickness versus the manufacturer's layer thickness. So that might change depending on what the new carbon fiber's layer thickness is.
But with the dimensions also, were they done in centimeters?
Yeah, most of the dimensions were done in centimeters, and we decided to change it to inches to make it easier for structures and manufacturing.
I think one thing, I think you want to be careful, to whoever presents with significant figures in the future. So if you present a lot of significant figures like that, you're telling, it's like putting on a requirement for manufacturers.
Yes, that is a good point.
Manufacturers. So typically, it's, not in good taste to put so many significant figures when you're presenting it.
Yes, thank you. We'll keep that in mind, and it's definitely important because we do not have our tolerances like grounded yet, so we can't get too specific yet. That's all for profile manufacturing. Then we'll move on to flight performance. Here are our performance goals. Target apogee is 10,000 plus 1,000. We have only have the margin above because we'd rather overshoot than undershoot. Because depending or based on what we see in the wind and temperature, angle of attack stuff, it can only go down from what we have it calculate or from what the simulation says. Maximum velocity 10,061. That's about Mach 0.95 at the launch site. That's getting really close to supersonic. Ideally, we're not going to hit anywhere close to that. And based on our calculations, we aren't there yet. So that's good. Testability, 1.7 to 2.0. That's just based on what our open rocket says. I think it was 1.92 before, or on our previous slides. I'm going to go into the motor specifications. This is kind of an internal requirement that we set for ourselves because we already have this motor. So the rocket was pretty much designed around it. It's the same motor we used last year, but the dimensions of the rocket have changed, which is why our simulations and stuff are giving us different apogee stuff. So average thrust is 373 pound-force, max thrust 501, burn time 6.23, launch mass is 19.82, empty mass 7.35. That's all from the manufacturer. And there's a thrust curve as well. And Tyler's going to come back here and do a rocket.
So for the open rocket model, we were able to achieve in the no wind model an apogee of 10,820 feet. As we're leaving the launch rail, we have a stability caliper of 1.5, which is great. Anything above 1 helps keep us stable. So knowing that we're leaving the launch rail already stable is great. at Mach 0.3, which is kind of the standard to measure against, we're at a stability caliper of 1.92. The max speed is almost 1,000 feet per second, which is below the Mach limit that we set of 0.95. So we know that we're not going to run into problems going transonic. Our max acceleration, 265 feet per second squared. And yeah, now it's important to note that this isn't the no wind simulation. Later on, we're going to have some weather analysis based on different wind speeds and what that looks like. But in the ideal case, we are looking good.
Okay, thank you. And I am here for the MATLAB function. This is a much less precise approximation than the open rocket because it doesn't account for wind and it's modeling the rocket as a cylinder. It doesn't take into account all the intricacies of the design. So altitude is 10,937, a bit higher, but still within our 11,000 range. Max velocity is 993, and Mach is about 0.88 as well at that speed. Max acceleration 243, time of apogee 25.2, flight time 250. Yes, Charlie.
What were the units of the acceleration? I think
Oh, I'm sorry. Yeah, there should be a squared there, feet per second squared. Thank you. There might be another mess up here. It should still be feet per second squared.
Alright, something we have not taken into account is kind of our angle of attack for the rocket. Just so, I guess I'll kind of go over this left side first. So the main simulation that was run, you'll see on the right, was simulated with the no wind condition, just so we can kind of isolate exactly how the angle of attack would affect our apogee. We found that increasing angle of attack lowers the apogee. So under the no wind condition, the optimal angle of attack was 11.5 degrees. So at 11.5 degrees now, the average apogee was then found to be 1,000 or 10,003 feet with a standard deviation of about 20 feet. So the average maximum velocity was 998 feet per second, and the average maximum acceleration was 266 feet. And average time to apogee was about 24 seconds. So angle of attack analysis, you can kind of see this was done in increments of 2.5 degrees. So for first at 2.5, we found the average apogee to be about 10,750. At 5, it was found to be right around 10,600. At 7.5, it was found to be about 10,400, and then it kind of started dropping more and more. At 10, it was about 10,150, and then at 11.5, it was 10,003. So that's just kind of show on that.
Do we know like what the angle of attack is at far, or like do we have an option of what the angle
I
is?
believe we were told we wanted to set it. That's from last year because we were asking, we wanted it to go perfectly straight, but they said there's no requirement to what the angle of attack has to be.
Okay.
And it also can change depending on the wind. This is shown, this is in the no to low wind. So a different angle of attacks may be used, launching into the wind.
Yeah.
Cool. Yeah. And also, if anyone's confused on what angle of attack is, that is the angle that the launch rail is set up at. So 0 degrees would be perfectly straight, and then 11.5 is tilted a little bit. And usually you just change that to account for wind, but we can also change that to help with our apogee. Thank you. And next is weather analysis. Oh, it should come up.
Hi, I'm Connor, and I'll be presenting the average weather conditions for the time of launch. And so after taking the average wind speeds and temperatures for the first week of every June since 2018, we found that our average wind speed for 12 to 3 p.m. was 16.5 feet per second. And for 4 to 6 p.m., it was 23.7 feet per second. And our average temp for 12 to 3 p.m. was 89.9 degrees Fahrenheit, with our average temp for 4 to 6 p.m. being 90.7 degrees Fahrenheit. And so after running these conditions with our open rocket model, we found that our average apogee for 12 to 3 p.m. was around 10,781 feet with a standard deviation of 110 feet. Our average max velocity was around 1,000 feet per second. Our average Mach acceleration was 266.3 feet per second squared, and our average time to apogee was 24.8 seconds. For 4 to 6 p.m., we saw an increase in both temperature and wind speed, which brought our average apogee down to 10,686 feet with a standard deviation of 119 feet. Our average max velocity was 999 feet per second. Our average max acceleration was 266 feet per second squared, and our average time to apogee was 24.6 seconds. And so after graphing these average wind conditions on the figure shown to the right, we also see that there's quite a bit of fluctuation between the averages amongst our 10 trials. And the reason why we chose 12 to 6 p.m. as our time frame is because Encore launches after Bebop, the air brakes project, and so we, need some time to take the stack off of Bebop.
And I'm gonna come up and do the next part of the weather analysis. These are the extreme, like the lowest apogee that would happen and the highest apogee. The minimum altitude would happen if there's a lot of wind and it's low temperature, because if it's hotter, then the air becomes less dense and it becomes easier to fly. So a wind speed of 30 miles per hour, that happened on one day, like 3 years ago, for a single hour. So that's not gonna happen, but still it's good to account for the extreme. Some temperature is about 70 degrees. That's the lowest temperature that happens there. So be ready for that. Apogee 10,108. That's still Ariel. Thank you. Let me. Where's the mouse? Can you read it to me, please?
Simulations given all of these different inputs.
No, we have not. Could you explain what that means, please?
Like what altitudes you get from different weather conditions. I think Monte Carlo is like a random-ish simulation, so just putting a bunch of random things together.
Okay. No, we did not do that. That is a good idea. The way that this was done was these wind speeds. We took the standard deviation from all of our data. It was about like 7 miles per hour difference. So it's quite a big spread. And OpenRocket was able to account for that. And then the temperature was about an 8-degree difference. OpenRocket didn't really account for that. That's the most that we were able to do as far as randomization goes. But we will look into that Monte Carlo simulation. That makes sense. That would be a good idea to do. Yeah, so back over here, apogee is low, 10,108, and then I don't need to read the velocities and accelerations again because it's about the same as it always is, 0.895. That's a little bit higher though. It's still lower than our goal. The max altitude is if there's absolutely the minimum wind 3 miles per hour and it's the highest temperature possible, 107.2 degrees based on our data. Also pretty extreme. This one does go above our apogee range, but as previously mentioned, as long as we're going above 10,000, we just change the angle of attack and it should drop it to whatever we want in the range. Maximum velocity, 10,000, or yeah, you can read all those yourself. Any more questions as far as weather goes? We're going to move on to bill of materials stuff. Okay. Aerodynamics, bill of materials. So a lot of this stuff is stuff we already have, but we did purchase the mandrel and the vacuum bagging valve. That adds up to about 125. All that stuff in the middle is donated. That's why it's $0. And this red one is also $0 because that's the one we're looking in to get from Huntington Beach. There is, if you go on the bill of materials, there's a link to the data sheet with all the information about that as well. Yes, so that's about everything we have for aerodynamics. Will?
So going at the beginning of the section for like performance,
Yeah,
starting with lock number, so you guys can lock in 0.95 here, and then later in your later simulations, it's like 0.88, 0.89. So I'm just wondering where you got this from.
that's the performance goal. That's the maximum that we would want it to be. Before we start like assuming it's supersonic, and then at that case, we don't really want to launch if it's gonna do that. So we're trying to make sure it doesn't go above 0.95. So all of our 0.88s are still within that that velocity, if that makes sense. It's still
Yeah,
under that.
okay. Got it.
Oh, sorry. Yeah, no, these are the goals, not outputs. These are what we want it to be within.
How was this goal or objective, target velocity or target lock number then calculated?
Yeah, that was to be completely honest, that should be the critical Mach number, but it is not because we do not have our CFD. I know that is very not good on our part. We are working on that still, and making sure that's perfect, refining the mesh and stuff, because it's a weird doing the cone. There's a lot of drag, and it's making the CFD more difficult than we initially thought.
But, and then I remember during PDR, I think your apogee was more toward, more high than 11,000 for the non-competition.
Like-
And now it's a little bit below 10,000. What changed it? I guess within the nose cone.
Yeah, most of it was changing nose cone, like the ballast stuff has changed because now we have to have water in there and a water deployment system. The fins have also changed shape. If you remember before, they extended like past the where's the full design? They extended further past the end, and they would have been resting on those like 4 points, which was probably not a good idea for to have 4 points hold up like 55 pounds of weight. So this should be flat on the ground now. That changed. The length changed a little bit to account for different the subsystems needs. So like recovery, the length it was based on that. Avionics was based on the avionics stack that has to fit inside the smaller air brakes rocket, Bebop. So we limited the avionics to that same amount. And then, yeah, that's about all the changes mostly.
I find, yeah, the angle of attack analysis and the average weather conditions, that analysis was pretty insightful. Expanding, like Matthew said, with the Monte Carlo simulations and building out like your probability, so you get like your like 98th percentile, like
Yeah.
what you expect within that range. Would be, yeah, would show further insights. I was wondering, okay, so with all of this like simulation done, and the analysis, you know, showing that it was off, that rocket would be affected greatly by temperature, which was great analysis, by the way. What would be your like approach moving forward? So would you vary angle of attack? Like if it was a hotter day on launch day, like would you go up to Rick and say, hey, we have a greater angle of attack? What's your
Yeah.
thoughts on your approach?
Yeah, that's mainly my approach. So as far as these like weather simulations and stuff go, averages can only do so much because there is like standard deviation to account for. And as you can see, the spread is quite different depending on the day. So the best we can really do, Open Rocket lets you turn off standard deviation and set that to 0. So it could check the exact wind speed and temperature you need, and it won't have any deviation on apogee wise. So what we will probably do during launch day is look at the temperature and the wind speed that is happening at that launch time that we're planning on. Plug those into Open Rocket, and depending on what it is, let's say it's like 10,500, based on those wind and temperature conditions, then we'll account for that by changing the angle of attack by like 5 degrees roughly. Yeah, I was planning on setting it exactly to the simulation, or at least still above, not like 9,999.9, but like 10,005 or whatever, however close we can get it. As you saw on the angle of attack side, like the closest we can get was 10,003 roughly. And the standard deviation, in our no/low wind, that's like 5 miles per hour. It has very little effect on our apogee. So yeah, if we turn off the standard deviation stuff from the wind speeds, then it should help us get a more precise estimation. As far as I could see all across the internet, OpenRocket is the #1 source for amateur rocketry estimates, and the calculations that they get there are pretty close from like forums. People are saying that OpenRocket has gotten them pretty close to what they wanted their apogee to be. And I know pretty close is kind of vague, but it's like, it depended on the person, whoever said it, and how high they were going. Because like 100,000 feet and it went 900, or it went like 9,000 or 99,999. Like, that's not likely. But if it was like within 1,000 feet, that's a good margin for them. Whereas 1,000 feet for us isn't as good. So yeah, that's about what we were planning on doing.
And my last comment would be, I think you guys should look in the weather conditions. You guys should look in the morning just in case. For the air brakes project, we're having some problems ordering the motor, and we might have to do it there. We might have to order it directly to the far site and assemble it there. So just in case, we're still trying to figure that out. So what I'm saying is look into the morning just.
Okay, we might launch first. I thought, okay, never mind. Yeah. So new news, we might launch first. So we are gonna redo these with 8 a.m. to 12 p.m. as well, so that we can account in case we're launching earlier. Thank you for bringing that up, Ariel. As in like what is keeping us, or like why we don't want to? It's mainly structures, because as we're gonna bring up during structures, the numbers on that are looking a little iffy based on the material that we have. And then going supersonic will introduce the shocks and other forces that we will have to account for. It just will make it more complicated, and our structures team probably does not want to do that. So yeah. If there's more structures questions, I'm gonna be back to talk about structures as well. But yeah, if there's no more aerodynamics questions. Our lead is in the chat right now. She could not come today because she's sick. Elizabeth, say hi if you're here. Otherwise, Calvin is gonna be
Hi.
here. Hi.
I'm Calvin, and I will be presenting structure slides today. So here's our full CAD model, both put together and then also apart, assembled. The first thing we're going to talk about is the motor mount. So it's going to be a 98 millimeter cardboard tube, which is 3.858 inches, a length of 36 inches, which is more than the motor, so we're good on that. And the wall thickness on that's going to be 0.1 inches. We'll attach 3 centering rings made out of plywood with an inner diameter identical to the diameter of the cardboard tube and an outer diameter of 5.984. The thickness for those will be 0.5 inches. And then we'll have our fins slotted in between the bottom 2 centering rings. And they will be epoxied as well as with the centering rings to the cardboard tube. And all of this whole assembly will be put together and then slid into the body tube. In terms of couplers and bulkheads, we'll have 3 couplers and 2 bulkheads. They're all shown, I guess, in that figure there. 2 couplers are for the recovery system. And then there will also be a coupler between the motor mount and the avionics tube. Each of these couplers will have 4 M6 holes drilled perpendicular and then perpendicular to each other, and then they'll be secured using M6 bolts. And the safety factor that was calculated for each bolt is 15.2. Additionally, we'll have 1 bulkhead to secure the avionics tube,
And then another one to stop the motor from flying into the rest of the rocket. All of these will be constructed with 6061 aluminum. This is the assembly for the motor mount coupler and avionics bulkhead. Like I said, they'll be constructed using aluminum. The bulkheads will be constructed using aluminum rods, and then the coupler in this case will be constructed with an aluminum tube. The length of the bulkheads are identical on each side. They'll each be 0.748 inches in length. The diameter of the wider lip will be 5.984 inches, and the diameter of that narrow extrusion there will be 5.591 inches. The coupler will be 5 inches in length with an outer diameter, or those should be flipped, an outer diameter of 5.984 inches and an inner diameter of 5.591 inches. For the recovery pressure vessel couplers, there will be 2 of them. The outside profile will be identical, but the inside, like, bulkhead-ish will be a little bit different, and Ariel will talk more about that in the recovery section. But there will be a 0.1 inch groove for an O-ring. The upper coupler will be 3 inches in length, and the lower coupler will be 5 inches in length. And those inner and outer diameters are identical as the motor mount coupler as well. At the bottom of the rocket, we'll have a motor retention plate to stop the motor from falling out on descent. It will also be made out of 6061 aluminum with an inner diameter of 3.7 inches, an outer diameter of 5.984 inches, and a thickness of 0.5906 inches. And we will have 4 M6 holes drilled 45 degrees offset from the fins so that they don't run into them when we're screwing in the plate into the body tube. And the safety factor that was calculated for this is 14. Rail buttons were an issue last year because we used 1010 rail buttons, which is for a 1 inch width launch rail when our rocket needed a 1.5 inch width launch rail to launch off of. So this year we will be using 1515 rail buttons to not let that happen again. We will either be using the standard rail buttons or more aerodynamic rail buttons for less drag, because those are what's in stock right now. The rail buttons will straddle the center of gravity, with the lower one being placed just above the bottom centering ring in order to easily load the rocket onto the launch rail. And the upper rail button will be located just below the recovery bulkhead. And we need to make sure to place these in between 2 fins so that they don't interfere when we're loading onto the launch rail. And these rail buttons are taken from Apogee Rockets. They're reliable, the website, and far recommended as well. For material, oh yes.
For rail buttons, I guess, and also motor mount, do you have manufacturing plans? Because I know last year those 2 were like kind of bad putting in, like,
Right, so
I mean, like, in terms of like actually how you're going to get the rail buttons in there, because last year we did a jank little magnet way of getting it in there, and I don't know if that's gonna work.
we do not have manufacturing plans yet. Yeah, because both of these spots are not the easiest way to get to. So we'll definitely have to look more into that. But there is like a pin on the bottom that goes like in through the back end. So definitely looking into putting that pin in and possibly epoxying it to the inside of the body tube before we load everything in. So then when the time comes, we just have to throw in the rail button and then screw it in on top. I think that's the best way that I can think of right now, besides what we did last year, which isn't ideal. Yeah, last year we put like the real button in after doing the motor mount.
Yeah.
It was not a
We
good
used a
idea.
magnet to get
Yeah,
it, and that was not good.
somehow it worked.
And then the motor mount shouldn't be too bad. We just have to, again, make sure we put that in after everything else. For material justification, we're using 6061 aluminum. It's been used on many different things, such as pipelines, aircraft, and automotive parts. It's reliable under large amounts of stress, and it has a high strength to weight ratio. Additionally, it's an easier material to work with in the shop, so that'll make the manufacturing team's job a lot easier. We also have some extra aluminum in the hangar that we could possibly use to save costs as well. For fiberglass, we're going to be constructing one of the body tubes out of fiberglass because even though it's a little less, it has less tensile strength than carbon fiber, we need it to allow the radio signals from the avionics section to go through because carbon fiber blocks the signals, so we wouldn't be able to get anything from avionics if we use carbon fiber. And then carbon fiber, we've had experience with strong, low density, and easier to mold.
Okay, and now I'm gonna be, thank you, Calvin. You're gonna have to come back after this though, I think. So I'm gonna talk about the testing that we did. These were, like I mentioned earlier, about 3-inch diameter tubes that were the short one, or the small one, we were recommended to do about 1 inch tall. The medium one was our 3-inch one, and the long one was about 7-8 inches. So as you can see from the carbon fiber, it does not look good. So the results of our compression test were 70 megapascals. The manufacturer data says the compressive strength should be 552 megapascals. That's like not even a fifth. It's like an eighth almost of what it should be. This is probably due to the freezer, or we just did a really bad layout. Considerations, the wall thickness was greater than fiberglass samples, so the wall thickness was about 0.3 centimeters. And our thing that or the actual one should be about 0.23. So it was a little thicker than it should have been, but I don't think, or the fact that it was thicker and the fact that the compressive strength is like bad still, like way underneath, I think making it thinner wouldn't help our case, because that would be counterintuitive. New donated carbon fiber, like I mentioned a lot, Huntington Beach has carbon fiber just waiting for us that we have to go get. Hopefully someone will be able to get that soon, as soon as possible before we start actually manufacturing. And up in the corner is the maximum loads that the press, or the composites lab hydraulic press was able to do. It's about 50,000. It caps at about 50,000. So all the carbon fiber was able to withstand the maximum. It automatically stops when it's approaching the maximum. So it was able to survive all of that. It just did not have good compressive strength as shown by those numbers and the graph down there. The part itself did not have any visible damage when we took it out. All three of them seemed like they could have been crushed even more, which is not the case for this upcoming one. The fiberglass results, compressive strength 27, manufacturer 480, not good. So we are probably going to use wet layup fiberglass from the cage because most important thing that apart from these numbers being very low considering what the carbon fibers were, is that there was visible damage on all the fiberglass. They were just crunched up and they were peeling off, or the layers were peeling off. We were able to completely unravel it after only 5,000 newtons of load, which is about 2,000 pounds for the Freedom Unit people. Yeah, so wet layup using fiberglass. We're gonna do more testing, but I think that fiberglass is done for. There are the graph numbers, and that's about all I've got for composite testing, if there's any questions on that. Oh, and these walls were about 0.1 millimeter, 0.1-ish, so they're about half as thick as they should have been. That is another thing, the thickness that the manufacturer gave us for these fiberglass is way less than it actually turns out to be. So we thought it was gonna be 0.74 millimeters, which would only take 3 layers to do however thick we need it to be. but it actually was more like 0.26, like a third of what the manufacturer said it was gonna be. We ran into that issue last year as well. We just did another wet layup over that to make it thicker. That's everything for composites. There's no questions in the chat. Okay, cool. Calvin, you're gonna have to come back to these calculations. Oh, Ariel's coming up now.
Hi, I'm Ariel. But so for our structural strength calculations, we did, our first one is the rocket expression compressive loading due to aerodynamic forces. So our safety factor for fiberglass failing is 17.5. The compressive strength is 35 megapascals. For our carbon fiber, it's 35.2, and our compressive strength is 70 megapascals. And our safety factor for to fail in collapsing failure mode is, so you have like the length over the diameter value, and this is greater than 15, which is good. So our minimum length of our rocket needs to be 92.126 inches, and our actual length that we got based on this number is 92.126 inches because we had to shrink it down. And then our ratio of the diameter to the thickness is greater than 70. So based on this, we changed the wall thickness. So our minimum wall thickness is 0.091 inches, and our actual wall thickness is 0.098 inches. So moving on to the bending moment, on the left, or you can see the shear and moment bending diagrams, shear and bending moment diagrams. And the wind generated by the wind generated by the wind creating normal forces. So the wind generates normal forces that act horizontally to the rocket, which is where we're getting those values over there. This is acting on the nose cone, the fins, and transitions. Transitions include like couplers and the bow tail. So the maximum angle of attack is 5.5 degrees, and our safety factor for fiberglass is 6.8. Our yield strength is 30 megapascals, and for carbon fiber, it's 0.68, and our ultimate yield strength is 40 megapascals. And here is our bill of materials for structures. The top two, we have a lot of spare aluminum in the cage from last year still. So we're just gonna have to spend a lot more time trimming down the diameter. But that should take off at least like $400 worth of stuff, which would be great. Questions? Okay, should we move on to recovery? Or-
Sorry, I kind of missed it for the bottom part of slide 43. So I think 2 slides ago, L over D and D over D. So it's L over D with drag and drag to thickness.
Length, diameter,
Yeah.
thickness.
Sorry, Karen.
Oh, all good. All good, yeah. So that's the length of the entire rocket and the diameter of the rocket. And I think the length is actually a little bit different than that, but in the good way. I don't remember.
In the good
In the good way. It's still above, yeah. It's below, right? It's gonna
Yeah,
fail.
should be
Yeah, it's still below, but it's like 14.9 something instead of 15. And then the diameter thickness, that's fine. Yeah, this is more for leadership. Are we allowed to use that 7-inch stock to make a 6-inch thing? We're gonna have to trim it down, but like,
Of aluminum.
yeah, I don't know if, because it's either $400 or we use that stuff from last year.
Yeah.
And that stuff from last year can be used for bigger rockets, like if we do another one next year, that's 7 inches. So if you want to hold on to that, then we'll buy more, but I would like to use that, so we don't have to
We
spend.
will have more money to buy 7 or 8 inch aluminum. This year we use what we got.
Got it. Yeah, so that $400 on the bill of materials, scratch that. We don't have to buy that. We can just use the one that's in the cage.
Also commenting on the section in general, I guess once again, significant figures, would be nice
Yeah.
to turn that down, especially in the coupler, dimensions. So I know, structures, specifically wanted to use like pitches and, imperial. So I'm just wondering what, dimensions, where is it the lengths that you wanted to use that for? And
I think, yeah, we had it in lengths right now. Did you guys want us to switch over to metric? Because I mean, on my slides, I have both.
I'm just curious.
Yeah, I think the weird dimensions are in like the thickness and diameter, and that's because we did ours in centimeters. So transferring that over, then it made it kind of weird.
I see. So when you manufacture, yeah, once again, with the significant figures, don't put like that many significant figures unless we were actually intending on like manufacturing.
Yeah.
Like the couplers to that dimension, which, yeah, it's pretty unrealistic, I guess. Let's see what else. For the composites testing, so you mentioned the carbon fiber, it did like actually break.
Yeah, you could hear like a little bit of noise coming out of it, and it could probably survive more than 50,000. That was just the max it could do. But taking it out, there was no visible damage like the fiberglass was.
Did like the Instron though, did it like let up, like did it like it stop compressing? Like at that moment when you heard that noise, or like did you guys turn it off, or how did that?
No, it kept going. It was just like little noises, just like not, it wasn't splintering. Splintering is probably the best way to say it, but like it wasn't. Yeah, I guess it was like little splintering noises. And it did not let up. It just kept going.
Okay, so you guys just like manually turned it off after.
It stops itself at 50,000.
Got it.
So we just let it go to the 50,000. And then check the damage there. And then for the fiberglass, it wouldn't even get past like 10,000 was the most, I think, on the strongest one.
Got it. And you guys, the process for that, if you could expand, you guys just switched out the tops for the plates.
Yeah, so we switched those out for the plates. We put our tube in between there, brought it down to like lightly press again, or like within a millimeter of it. And then we told it to run, and just keep going down until it was either stopped or we had to stop it. Like the fiberglass, we had to stop since it was never gonna hit that, machine limit. If it hits 50,000 and goes over that, it's gonna break the machine because it's not made to do stronger than that. Yeah.
So if there's a safety factor of 35 with the carbon fiber, when it's performing poorly, why not use it anyway? Why use
Right.
carbon fiber?
You want to ask Elizabeth?
Elizabeth, what is that safety factor calculated off of?
So the safety factor on this slide is calculated on if there was no wind, it was just going straight up. And so there's a question also in the chat. So I was waiting for you guys to finish why we're okay with such that high of a safety factor and whether we could like thin the walls. So can you guys hear me okay, by the way?
Yeah.
Okay, cool. So first, to answer that question first of why we have the wall thickness what we do, if the wall thickness, like 'cause you can see at the very bottom the diameter, it should be the other way. I'm sorry, I've been sick. My brain hasn't been working. It should be the diameter over the wall thickness should be less than 70. And if it was over 70, the tubes may fail at a compressive strength that's lower than the yield strength. And so if it was, it'd be failing in a buckling failure mode, and that's not what we want because that could be a sudden failure. We want it in the collapsing. So that's the reason that we need the wall thickness what we do. That's why we need that minimum wall thickness. And then in terms of why we can't use this carbon fiber is this is for an ideal situation if the rocket was flying straight up. The other situation accounts for the bending, which would be from the wind. And most likely there will be wind. The wind that this is calculated at is at it generates an angle of attack for the rocket of 5.5 degrees. The average would be around 3.5, which still has a low safety factor, and it has it's using a different mechanical property of the carbon fiber than the other calculation is. Does that make sense?
Yep. Did you say there was a
Yes.
question in the chat? Yeah, it makes sense.
Yeah.
Was there a question in the
Okay.
chat or did you answer that too?
I answered the question in the chat.
Okay, cool.
Okay. I think we're just gonna move on to recovery then.
Yeah.
So that's me. I'm Ariel. So for our outer profile, we're making a pressure vessel again from carbon fiber. So that's gonna be our body tube. And then the two aluminum couplers on each end. There's gonna be a clearance fit, which I'm gonna talk about a little bit later, between the top coupler and the body tube. The bottom coupler is gonna be secured with 4 M6 bolts. Then there's gonna be an O-ring between each of the couplers and the body tube to create that airtight seal. And then for our through holes, we're gonna have 1 3/4 inch eye bolt located in the center of each coupler. And then we're also gonna have, for specifically the bottom coupler, we're gonna have 2 holes we're gonna have 2 Peregrine holes. And then we're gonna have 2 holes for the TD2 system, which I'm going to talk about later too, because this is a switch up from PDR. This is just gonna be another hole to drill to kind of secure it in. This is for our main chute deployment system. So for our 2 stages, we're gonna have, for our drogue chute deployment, we're gonna have the 2 CO2 peregrines, fill up the cylinder with CO2 gas at apogee until the top coupler yields. And then at 10,000 feet, the TD2 is going to separate and release the main chute. So this is a layout. This is the same as PDR, except for the bottom instead of tender descenders. There's another little system. So yeah, O-rings up here, body tube, jaw cord is like the big squiggle. The parachutes are in red, and then coupler is in red, and bottom coupler is in red. So for our calculations for carbon fiber, so this is ensuring it doesn't break on the way up, and also when we release the CO2 into the pressure vessel. So our ratio of the wall thickness to our diameter is 0.2711. And so we can determine from this, it's a thick-walled pressure vessel. So we're using the thick-walled pressure vessel equations. And so for our safety factor for carbon fiber yielding upon CO2 release at 10,000 feet exactly, we're going to have a huge safety factor of 37,449. So it's not going to break. This carbon fiber is pretty strong, so that kind of makes sense. And we had similar numbers last year. But so yeah, on the right, you can see this is kind of a depiction of a pressure vessel. That's a cylinder under external pressure and internal pressure. That's kind of how it's modeled right here. And so I also modeled it for like if we release CO2 at like 8,000 feet instead of 10,000, in case the rocket is like the angle of attack changes. So you can still see it's on the order of like 10 to the 4th. So we're good pretty much. I think I modeled it from 8,000 feet to 12,000 feet if CO2 is released around there. And then for before CO2, we're completely fine there. We have a safety factor of 1.3 times 10 to the 10th. So this is like before the CO2 is even released, and it's just on the way up. And it's just under like atmospheric pressure. So for our bolt calculations, we're using M6 times 1 bolts, and we're connecting the bottom recovery coupler to carbon fiber. So for our shear bolts failing from pure shearing, we have 5.87 as our safety factor. And for them failing from edge shearing, we have 152.24. For our shear pins, these are only going to be used if we create too much of a clearance fit and we need kind of something connecting the top coupler to the body tube. But so these need to fail after we release CO2. And so that's going to be a safety factor of 0.22. And that's good because it's less than 1. And then for them failing on the way up, that's 165,864. And then on the left, you can see kind of a depiction of pure shearing versus edge shearing and what that looks like. So for our clearance values, we have, so I put a quick note here that like shear pins may not be needed if the clearance is tight enough, but it's going to depend on manufacturing and how good we are on the lathe, basically. So our target clearance is going to follow the preferred mechanical tolerances for metric ISO 286. This is from engineersedge.com. But the recommended tolerances for, you can see on the bottom, it says like, local clearance fit provides snug fit for locating stationary parts, but can be freely assembled and disassembled. So we're using kind of the H7/H6 standard. And this gives us a tolerance of 0.001 inches of clearance. So for our coupler diameter goal, we're shooting for like 5.983. So then for our O-ring sizing, we are using our McMaster oil resistant O-ring. The inner diameter when it is stretched is 5.768 inches, and our outer diameter when it is stretched is 6.004 inches. The thickness is going to be 0.118 inches, and this is straight off of McMaster. But it is a 90A durometer rubber O-ring. And then these sizing recommendations are found from parkerorings.com and based on our coupler dimensions. So for our inner components, we first have our peregrine. So this is the same as PDR. We're using two peregrine kits from Tinder Rocketry, and they will be used to release the drogue chute, and they will just be on either side of the eye bolt. And I also did a quick check a couple days ago, actually, just to make sure everything's going to fit in there because of the smaller diameter than last year. But yeah, they will fit fine in there, even though they're around this size. But so we'll have plenty of room. But they'll release the drogue chute at apogee, and they won't damage recovery equipment because CO2 does not do that. And they will deploy once the rocket reaches apogee, and the CO2 will flood the pressure vessel again. And the pressure vessel will separate and release the drogue chute. And this is how they are set up, and this is how we're setting it up when we do our test in the props lab. So for our internal components, I mentioned earlier that we're switching from tender descenders. This is because they're sold out everywhere. So we're going to use one TD2 from Tinder Rocketry. This is the same website that sells tender descenders, except this is kind of their new and improved object that they've been working on. There's two different types. We're going to use the top one there with the bolt in the back, or the nut in the back of it. But they work similarly to the perm that we used 2 years ago. It's a pyrotechnic initiated release device, which it just bolts on the edge, the like surface of the bottom coupler, and then the eye bolt separates off. But these are the best replacement for previously used tender descenders. There's also some other options, but they're not as trustworthy as just using an eye bolt connection because they're not as strong. And considering we have a huge rocket and a huge parachute, this is probably our best option. So they're going to deploy with the altimeter since it's a height of 10,000 feet. The black powder is going to cause the eye bolt to separate off, and the drogue will be allowed to pull the main chute from its bag. So for our altimeters, we're using the same ones as last year. The stratologgers, these are far recommended, and we're using a standard 9-volt alkaline battery, and they're compatible with e-matches from MGAG Technologies. So each one is going to be connected to both CO2 canisters and programmed to sense zero velocity, and connected to each TD2 system and programmed to sense 10,000 feet altitude. So for our recovery calculations, these are slightly altered from our different mass. So for our chosen parachutes, we still have the same ones, 120-inch main chute and then 30-inch drogue chute. We're reusing our previous parachutes to save on money. And they have a high coefficient of drag and small packing volume. Our ground hit velocities from apogee rockets equations is 4.77 now, which is like a change of 0.02. From our open rocket simulations with no wind, it's 4.5 meters per second. Our drift, we calculated for 5 miles per hour winds is 4,679.5. feet, and then you can see the metric equivalent. And then for 30 miles per hour wind, which hopefully we won't fly at, is 2,807 or 28,077 feet. And we also checked into this to make sure FAR has no requirements for maximum drift, and they don't, so that's good. Our shock cord length is 25.9855 feet. And yeah, I should change that for sig figs. But our packing volume is, we have 14,492 centimeters cubed available to us. And for our largest components, and this is our shared parachutes and shock cords, that is 4,553. And our rationale for this is to overestimate the volume because we ran into issues last year. Yes.
Two questions.
Yeah.
That's like 5 miles, right? For the 30 mile per hour? 28,000 feet?
Yeah.
Like 5 miles?
Yeah.
Okay. We're not launching at 30 miles per hour, so
Yeah.
that's good. And also the ground hit velocity, is there a like safe ground hit velocity, like a estimated?
Yes. I believe it's 4.5.
Okay, so we're like
Yeah.
right around that.
Yeah.
Cool.
It's around there. It's not an exact number. I think it's like a range of 3 to 5 miles per hour, but it depends on the source you check. Yes.
What is the angle status of these, purchases
Oh, yeah.
of using them?
I will talk about it on the next slide. But yeah, we took a look about a week ago. It turns out we have an even bigger parachute already in the cage. And then we also have an 84-inch one. So we have 2 backups if it's too tangled, but we are going to detangle like at least a week prior to launch. So for our parachute materials and preparations, we're gonna detangle the parachutes again. There's a bunch of different resources on Fruity Shoots detailing how to detangle parachutes. We're gonna go through these. We're gonna teach people how to fold a parachute, which is a Z folding technique. We're going to show how to pack the Jorgen main chute in the recovery section. And we're gonna use smaller quick links and duct tape so they won't crash into the body tube this year. For our materials, these parachutes are made of lightweight 1.1 ounce mil-spec calendared ripstop nylon. This is directly off the website that we bought these parachutes from. This makes parachutes more compact and lightweight, and they're zero porosity and resistant to mildew and rot. And they can be used again, but they're very reliable. And so for our propulsion lab testing, we're going to do the TD2 testing late winter quarter as soon as we get the procedures done. We plan to have the procedures for PDR or CDR, but because of the switch up we had to make for the 10A descenders, these are not done yet, but I don't think the process should take too long. The safety trainings will be given by me and Peter. And we'll give the propulsion lab safety briefing and black powder safety training. And here's a little video of what.
That doesn't work. You're not use the mouse.
Yeah.
Okay.
Oh, there it is. This is kind of how a test is run. This is what.
It's not showing.
So obviously they put a cinder block on the, wait, okay, do you have to drag it?
No, I think it's, is it showing?
Is it showing on the?
It's like a yellow screen with a video on the front, a YouTube short.
YouTube short. It should be this one. I tried to avoid using the YouTube short.
Yeah, it's showing the yellow
Okay,
screen.
nice. But I'll just play this. I'll just zoom it out. They put,
Really small though.
okay.
This is what we're seeing.
So,
Sorry, everybody in person. I can turn my laptop around, but
okay.
I don't know how to get it to go over there now.
Okay.
Here it is.
So that's how it's connected. We're not gonna place a huge cinder block on the bottom of it because that's not really necessary. But yeah, it just separates like that. And then the E-matches are connected like over there. It's like a pretty simple test to run. It's really similar to the time descender test we ran last year. Just looking at it to separate.
It says y'all have many parachutes strewn about of all sizes.
Yeah. Yeah, we got a lot. I just found more. A huge box. Okay, and then for the pressure vessel testing, this is early spring quarter once the whole thing's done and manufactured. And this is ensuring the top coupler successfully separates from the body tube in a safe manner. We're gonna go by the same safety regulations that we talked about earlier. And the procedures for this one are ready, so that's good. Okay, so for informal testing, we're gonna do a drop test. This is just dropping the parachute with the load attached to ensure that the parachute fully opens. This is similar to the drag test that we're also gonna do. You can see the fun little picture right there. We did this last year. It's really fun. You just attach it to like a belt and then you just start running. And you just like ensure it's not tangled and not going to, and then it just unfolds. And like, it's also a good way to test that you know how to fold the parachute. So then in early spring, we're also going to do a pull test, which is just shown right there from BPS's Space's recovery system test. This is just assembling the whole thing and then pulling it out to see if the shock cord connections are right, because the shock cord connections are probably one of the most complicated parts of recovery.
Fabulous.
Yeah.
Comment. He said you should add a load when doing the separation test.
Okay, so like the cylinder, there's probably stuff in the props lab. I'll just grab and put them on there. So then our bill of materials is shock cord. We have a bunch of this already, but we do not have enough for both rockets. So we're just getting one more section of it. And then we realized from doing inventory that we need 3 more CO2 canisters to be able to perform the pressure vessel tests and launch for both air brakes and for Encore. So we're buying 3 more of those, and then a housing cap assembly because epoxy got on the other one of the peregrines, so it kind of made it unusable for this year. And it's just permanently stuck in the bottom coupler. So yeah, if we're buying one of those, you can just order these parts off of Tinder Rocketry. It's super easy. They come individual. So then we also need more E-matches this year because the whole club has been just collectively using ours. So we're just gonna get 2 more packs of those, which is 20 in total. So that's enough for testing and for launch and to have extra. And then for our O-rings, we're getting a pack of 10 from McMaster because they're just sold in packs of 10. And this will allow us to have extra because I know last year when we were doing it on the lathe, we ended up making some O-rings unusable because we were trying to gauge them for sizing. Okay, so for our next step, order materials is the big thing. And then finish our routing sheets. We can actually do these during body tube manufacturing, but just before we're starting out on the lathe. And we're also going to finish the TV2 test procedures and send both procedures to the tourists. And then we're going to schedule the propulsion lab testing once our pyrotechnic arrives.
Thank you.
This is a quick question, your calculation, so.
Yeah.
That was assuming that, the rocket shoots perfectly straight up without any angle of attack.
This is with 5-mile-per-hour winds and then 30-mile-per-hour winds.
Okay, but
But
without
like,
any angle of attack.
yeah,
Okay, got it. You might want to check to see how angle of attack might affect that.
okay,
If you were to launch at like 5 degrees, for example, that might make it more annoying. If
Yeah.
we're out there. And then if it is like heavy winds, since it would be like so far, I guess that could act as another consideration for like we should go first. Then if we walk at like
Yeah.
10 minutes per mile, then, and if it's like 5 miles away, for example, you know, there is that. But yeah, other than that, yeah, nice.
If we launch air brakes first, it will not go that far.
Yeah,
We want to do our trek at the end.
yeah, probably, because then we would have to take time for the trek and then to transfer and that might get pretty.
I don't really want to do a 10-mile hike in the desert, so we're not launching if it's 30 miles per hour wind. I'm calling it there, like.
I mean, we could use a smaller chute. 84 inches and that's safe though, so.
You think they'll let us launch it? I don't know. I don't think so. Hopefully not.
I mean, I'm fine with doing a 10 mile trek, just as long as it's at that end of the day.
Okay, you can go get the rockets then, Will. We'll wait for you.
Okay.
Thank you, recovery. And I'm gonna real quick just update the PowerPoint. Because there was a little change made. Oh, wait, stop sharing.
Hey, my name is Spundin. I'm lead for Comprocket Avionics. So just to begin, to remind everyone, we're aiming for a transferable stack. So regardless of if the air brakes rocket launches first or the or our solids rocket, both a solids rocket, like rockets. But if our 10K rocket launches first or our air brakes rocket launches first, we're able to take the stack from one and put it into the other. And we're not planning on transferring air brakes to, it's just the avionics, like electronics. So we're not too certain about plate mounting yet because we haven't totally finalized PCB dimensions. We're rather close though. But regardless of if we're vertically mounting or horizontally mounting, we're planning on 2 to 3 plates. One plate will be our primary PCB with all of our sensors. Another plate will be our antenna and RF module. And then we'll have another section for batteries and power. And that's last year's stack for reference, for if we aim for a horizontal mount.
So as far we're basically planning on having 3 IMUs and 3 altimeters. Those are the sort of the most key components. And when you have 3, it allows you to have redundancy if one of them goes out, because you can just take the median of the 3 data inputs. So if one shoots really high or really low, you still get the correct data. We do have a complete wiring diagram. This is just the one from last year for reference. We do have the actual one on the next slide. So we are just TBD on what the actual antenna and transceiver is going to be. It's like if theoretically we are able to get the transceiver from the stack from last year, which seems unlikely, we do have a plan to use that. But we also have a plan to use the Adafruit LoRa transceiver, which can also has a receiver mode, so that works well on both ends. I think we did end up, we were able to choose a camera. Although
Yeah, that's a little outdated.
Yeah. Although we are probably going to keep that separate from the actual flight board, and that's going to have its own separate antenna that comes with the camera.
And just to be clear, we're aiming for 3 separate camera systems. Cameras are typically 120 through 160 degree field of view. For FPV racing drones, we're using those cameras. So 3 of them provides 360 view. We want to not run them through the TNCs because video takes a lot of data. So we're having separate ground to air radio kind of channels for each camera.
we're using the I2C mode on all of the IMUs and the Bosch altimeter, just 'cause it's more convenient, uses fewer pins and allows you to sort of combine some of the communication channels together. So that's just that. Here's the rough outline of the current flight board idea. We've got the second team isn't going to be super used for this avionics section, but it's important for the air brake calculation. We've got the GPS module. This is currently laid out with the RFD 900 put in, but the transceiver we're planning to use if that one can't be salvaged would pretty much go in the same spot and connect to pretty similar pins. We've got the two IMUs up top. We've got 4 resistors and the one change made from last year with the IMUs, we now have the gyroscope interrupt pin connected, which makes it a bit easier to interact with that so we can get angle measurements more easily, which is good for when we're doing comparisons and calculations for the air brakes. Bosch altimeter is attached to the same I2C channel as the second IMU. We have the two FAR altimeters. The FAR altimeters are going to be powered independently, or rather, they're not connected to the same channel as the rest of the sensors, which just start getting powered through the teensy, because the FAR altimeters need to be sort of connected sort of via wire. It's just kind of a niche that's set up the problem with the FAR altimeters. The other thing that's going to need to be powered separately is the transceiver, regardless of which one is used, just because it takes in so much more current than everything else, and it can't really be run through the teensy. And because of that, we have two separate sort of like transistors and diodes just for the reverse polarity protection, because that was a problem last year, I believe. It kind of fried some stuff. So we have that now. So if something happens in that, should be able to be safe from that largely. I think that's about it.
So here's a revised data flow / software plan. Now there are 2 teensies up there and 3 kind of processes up there, but what we should be focused on for CompRocket is this right portion, just the red software diagram. The left portion is purely air brakes. So only one teensy is going to be the kind of focus for CompRocket. We're going to prioritize development for that first to get sensor systems set up. But yeah, right teensy is the sensor teensy. That one collects data and it distributes it to wherever it needs to go. So that includes transmitting it to ground and also sending it over to the other teensy. And the kind of data collection / distribution loop, that teensy will collect the available sensor data. It's going to avoid blocking on any of the sensors if possible, because the principle is we only collect sensor data when the sensors are ready to give it to us. So we avoid waiting for one sensor while others have updated data. So each of the fields in this kind of sensor data packet are going to be updated selectively, and the packet's going to be sent over on a consistent time interval. So yeah, collect the available sensor data from sensors that do have data, send it over to the math teensy, log it to the SD card, and also transmit it to ground, and then recollect. And that's essentially all of the CompRocket software taken care of. And talk about the airbrake software when airbrake CDR rolls around, I guess. As for our estimated costs, we're estimating around $520 for all of our components. There's a chance we'll be able to remove some of the components from the old stack. So for instance, things like the old Stratologger, which ends up costing a lot. We can take from the old stack and save some money there. But for the most part, the 2 most expensive items are our Stratologgers, as well as our long-range radio antenna. If we can find alternatives for that, or if anyone has any recommendations, they are most welcome, because as you can kind of see, those alone account for $200 to $300 of our projected budget. Pretty much all I have for avionics, if you want to discuss budget. Yeah.
Does that say you're getting 6 antennas?
Yeah, so we need separate antennas for each of the cameras because we have completely separate camera systems. Is that not the way to approach it? That was the plan.
No, it's 433 megahertz.
Okay, so you.
Although it does also,
Oh, I see. You have, okay, you have 2 separate. You have 6, 2 for each video.
Yeah, one for rocket, one for ground.
Okay. Um.
Okay.
If you can find them, figure out a way to use that. I don't know if that still counts for bars like rules on the 360 view.
Yeah.
That might save you some money because then you can only have like, you can have one transmitter instead of 3 separate channels. Which would require, like you're saying, 6 total antennas.
Mhm.
That might save you money.
The thing is, and it would be a bit of an annoying software problem, but we could collect frames at a lower rate. So refresh frames much slower and just use one ground antenna. That could also work. Instead of 3 independent ground systems or 3 independent simultaneous video feeds. So lower the frame rate. The video feeds will still be set like simultaneous, but they'll refresh much slower. And that seems like a way to do it. Yeah.
And then, do you have like software testing plans that, or are you putting some together for the, I guess both for air brakes and for this?
Yes. So as the first sensors that we're planning on testing are going to be the ones that we get from the stack because we're close to getting that. We've had talks with Trace about like doing that whole exchange. So we'll start testing that soon. We've been playing with teensy to teensy communication. That's just over serial. So sending a packet to one teensy, straightforward enough over, yeah,
and,
perhaps a pipe.
and we do have found libraries for most of like
Yeah.
sensors and communication with them, so it shouldn't be too much of a.
I would for sure, test the, air brakes PC by sending it data from another PC and just have like a set of what your like ranges of, your expected like maximum values are that you're getting on everything. And
Yeah.
just
Yeah.
making sure that it actually actuates the way that you want it to for all of that. Just because I can see there's probably a lot of unforeseen.
Absolutely, yeah.
Working with.
Mhm. But at least for Comp Rocket, we have pretty solid plans in place for testing sensors, just like we did last year. Yeah, set up sensors individually, kind of delegate them amongst team members, and they come back with like interfaces in the form of like functions written out. Yeah.
The 360 degrees is definitely the payload option, right? That's not a requirement for like to launch. It has to have the 360 degree. That's part of the payload.
Not sure what you mean.
Well, because there's the bonus points, like
Okay.
the drone one, or there's the requirement, like the water. The water was
Okay.
required. I don't know if a 360 degree camera is one of the requirements, is it?
Okay, toward the
might be
beginning of
bonus.
the slides. Oh, interesting. Okay.
I think it's just one camera. Just like one recording camera.
So is it one camera for bonus points or is it 360 view for bonus points?
360 view for bonus points.
So we're aiming for bonus points. Any more questions for avionics?
Cool. Coming back to do, thanks for avionics. Coming back for the final budget estimates. And let me also pull up what was approximated, what we're being given by the treasury. We're over budget, but we also, that's including the $400 worth of metal we're not spending anymore. So we're back under budget, which is good. We're given 1,541 roughly. We've already spent the aerodynamics money. And so the total cost is more like 1,200, and this is including all the avionics stuff is technically for both rockets. So that's if we need to, some of it can come out of the air brakes budget as well. It's your rocket too, Will. Avionics, yeah. So that's a lot of money for avionics. Hopefully we can get some of those parts back from the original stack. We think Trace has it and he has not responded when we have messaged him or we reached out to him. So we might have just walk up to him and just say it to his face. Yeah, so if we can get some of those avionics stuff, that would save us money. Recovery is pretty set. Aerodynamics is pretty set. It's just like about 400 off of structures and however much we can salvage from last year off avionics. But we are under budget. It should be about 1,200. Yes.
I'm gonna say, assume that you can salvage nothing off the avionics.
Okay.
Because we're not sure the status of the boards, and I know that, I think the Stratologger was Ryan Westcott's.
Okay.
And the video unit was also Ryan Westcott's. And the stuff that we actually paid for was all the stuff that was S&D components on the board, which are not gonna go salvage.
Right. But like, what about the antenna?
The antennas were off.
Okay, and can we get like the metal rods, the threaded rods off?
You can get those out of it.
Cool, so we
And all
could
the
just,
plastic parts were ours as well.
okay,
It
cool.
was just those two like most expensive components,
Right,
unfortunately. that
yeah.
were ours.
No,
Yeah.
that's fine. As long as we use the structures money or the structures, yeah, as long as we don't spend $400 on metal if we don't need to, we should still be under budget. Is that satisfying amount of budget talk for you, Will? Cool. Now we're gonna do a bit of schedule stuff. Gonna do manufacturing all starting as soon as possible. We're probably gonna have to do some of the wet lab stuff first since we have that, and until we get the new material from Huntington Beach. We're gonna be manufacturing all until May. During roughly first, second week of May is when we're planning on doing assembly and integration. Testing all throughout up until the go, no go date. We're actually gonna have one this year instead of staying up until midnight the night before we launch. So we're gonna, the week before, if it's not done, we're not launching. We'll just launch next year. Trip finalizing that last week before competition, and hopefully we can just have a smooth competition where the rocket's already been designed. We tested everything, made sure it all fit together. We just go over there, we launch it, and then we hang out. That's scheduling plans. Any questions for that? Nothing in the chat?
Oh, can you ask questions? I think avionics, sorry, I missed those. What testing plans do you have pre-launch? And then have you finalized what you will be using for your operator station software? I know in the past you were considering OpenMCT. Is that still the plan?
We are still considering OpenMCT, yeah. We haven't done much research into OpenMCT.
Can you come talk to?
Yeah, sure. I can. Sorry, I forgot the. That's Tanuj, right?
Yeah.
Yeah, we are still considering OpenMCT. Cameron, for booster, are you using OpenMCT at all? Okay. All right, cool. So I suppose the plan is OpenMCT, but if not, essentially all we need is a way of displaying the packets that we get in perhaps a terminal and displaying video. And those two should be rather simple, separate programs perhaps.
You can get it to output the JSON. Type it into OpenMCT.
Yes, okay. All right, cool. So yeah, that's the plan for visualization on ground. You also asked about testing. Right. So do you mean for air brakes and comp rocket or just comp rocket? Because for comp rocket, testing individual sensors is straightforward enough. We have an IMU connected to our board, and we have a bunch of other sensors connected to our board, and we kind of move the board around and see if the readings like seem reasonable. I suppose if we feel comfortable enough, we can like toss our board up into the air a few times. But really, we just want to make sure that we're getting input from the sensors. We're relying on the sensors to be developed reasonably, I suppose. Yeah. Do you maybe want to elaborate on that? Like, what type of testing do you mean? Are you watching the chat?
I'm watching the chat. He also asked what caused void failure? Oh, wait, I would definitely make sure you do antenna testing and getting a general idea of range.
Oh, yes, definitely. Yeah, I suppose that would consist of one person like hikes up to the P, and another person hikes up to something else, and we see if we get packets, from one to the other.
Yeah, what caused board failure last year?
Yeah, so as I understand, as I understand it, part of it was, like reversing polarity, right?
Well, so
Um,
we have one board that we built that blew up, and then we had to rebuild the board. Yeah.
We talked to the alumni.
Hello.
Okay, you did do that.
Issues with the board last year. We had one board blow up, we rebuilt it, and then that one wasn't working, so we built another one. And we think that over multiple solder paste applications, we just had some like bridges and stuff, and we just couldn't get it to get data off of I think it was the IMU. So that was our issue last year, to my knowledge. I haven't been able to actually like look at the board this year to like confirm that, but that is my assumptions.
It just blew up in quotes.
Yeah, well, there's magic.
we tried the little magical elves running the machinery, and sorry, any other questions or? Thank you.
Waits for SMD stuff.
Sorry, SMD stuff?
I don't know, sorry, I'm just.
No, yeah, sorry. I just like you're kind of the interface to Nuge. Okay.
Yeah, that's great, put them on, I'm assuming you can, but don't yell.
Okay, I'm not a very like electronics oriented person. What do you mean by SMD?
All the components on your board.
Oh, got it. Okay. Cool. Any more questions? Thanks.
Tanuj said he would, that we should consider using hot plates, because he used one in the EE building. So that might help. Okay, I'm gonna go back to schedule. Any questions on the schedule? Manufacturing is planning to be done concurrently with air brakes, which is gonna make a little bit, it's gonna be a little stressful, but the estimate for how long it would take to build one rocket was about, or it was like being conservative, like 7 weeks, and we're on week 6 of spring, so we still have, and we don't launch till week 10 of week 9 of, we're week 6 of winter, and then we launch week 9 of spring. That's still like 15 weeks. It'll only take 7 if we're really good. But assuming we're not really good, it's probably gonna take the full 15. It's 14. That's what, yeah, testing and troubleshooting and all that stuff. If there's no other questions, yeah, thanks for listening. Here are our sponsors. Any final questions? Nothing in the chat? Okay, thank you all for coming then. If you want to talk to me after, then I'll be here.
Great job.
Thanks, Matthew. Bye. I'm gonna leave. I'm gonna leave the Zoom. Oh, it's Will.
Oh, wait, they left and didn't even say bye, okay. So-
They really just, Matthew said great job.
Enthusiasm.
Ryan, I have 2 cats. Oh, wait, actually. I did a lot of things. So this was manufacturing. Less lovely stuff. Me and the systems team.
Which should have been.
Because like. Somebody needs to be more. And we can help out.
I'm so tired.
That doesn't mean you have to be
No,
able
I'm
to
not.
do it.
I'm just responding to getting. Yeah. I'm the kids. Yeah, it's about when. Like today, that's yeah. No, no, I mean, yeah, I'm not. So 15 minutes.
No, I knew, I was like, when that shit was not in the freezer over the summer, I'm like, they're gonna get such shit data.